applications, specifically in ray tracing. So here are the main ideas that I'll be going through. I'm going to first explain what rendering is really, how ray tracing sort of fits into that definition, and how Kajiya's rendering equation relates to all of that. And then I'll go through a quick demo on how it's applied. So what is rendering? Well, rendering, as some of us might know, is how we put an image onto a computer screen. So let's first think about how we generate images in real life with a camera. So we have some organic source of light, which is usually the sun or something like a light bulb or these lamps. These light rays go into the scene, they bounce around, and they hit the film on our camera. Usually we can control some small size hole and use that to focus the camera and stuff. However, when we're trying to simulate this on our computer, we don't have the advantage of having organically produced light. If anything, we would have to compute the light rays that go into the scene. Additionally, we also have to provide information on where objects are in the scene. So in this example here, you would have to simulate a camera. This is the viewing plane, and this is what's projected onto your screen. And then these are some things you would define in the space ahead of time that you would want to render or project onto the screen that you see. Now, in order to put things into perspective, one of the things I'll be talking about is how rendering can be really expensive in terms of computational cost. So what does this mean? What does it mean to be expensive? Well, as we know, we have screens, and screens have aspect ratios. What does that mean? There's some ratio in terms of the length and the width, and in order to have visual clarity, we would need more pixels. So here we have an example of something like a 4:3 aspect ratio with only 256 pixels. As you can tell, you cannot understand that these are circles or spheres nonetheless. Here with 1 million pixels, you can think of this as like if you're on YouTube, if it's 480p, you're gonna have the same aspect ratio for the video no matter what, but 480p looks pixelated, you can't really understand what's going on. So then you click the thing and you go 1080p, and boom, you get a clear image, right? But if we think about in movies and stuff, they're usually in 4K or 8K, they're rendered at these way larger resolutions, and those have like 22 million pixels. So imagine if we had to generate rays of light for 22 million pixels, and we would have to wait for, if I go back to this diagram here, we would have to wait for this light to hit this film on the camera. Most of these rays are going past the camera, so that's already too expensive. So how do we do that? Well, before I go on to that, in order to explain ray tracing, actually, I'll come back to this. So I would first like to explain two types of rendering. So we have rasterized rendering and ray trace rendering. The thing that I said was the most expensive was calculating light. So one method of doing rendering, which is a more simplified way of doing it, is using the rasterized method. The rasterized method is a way of, if we first define the properties of an object, and we sort of ignore light. So we say, what color should it look like, what it looks like in the screen, and you get this more basic visual image. If you remember those early days of building websites, and you would have these like physics models, and it'd be really badly rendered, that's usually what they look like. However, if we want to simulate light and get these more photorealistic renderings, that's when we would have these ray tracing. And so ray tracing, best understood, is sort of if we want to give things a proper geometric shape, we would have to somehow simulate light. So how do we do that? So let's go back to my definition of how we created images initially, and that was with the camera. So how do we attack the problem of making this efficient so that we don't have all these light rays that don't really give us any information? If we were to do it from these natural light sources, it would take forever as we wait for these light rays to populate the film and eventually every pixel. So instead, what if we work it backwards? What if we instead project rays from every pixel on our screen? So the idea behind this is that we're not gonna wait for these light rays to hit our film. Instead, we're gonna look for potential chains of light that bounce around and actually give us information. And this guarantees that, because we can always calculate whether or not these actually hit light sources. And I'll get back to that as I talk about its applications, but keep in mind, right now we're going backwards. So instead of generating rays from light, we're generating rays from a camera. So I know this looks scary, and we just went through a lot of heavy math, but I'll try to break it down for you guys. So this is putting it into simpler terms, and as you'll see, there's 4 main components to this formula. This essentially is a way to measure reflected light, the behavior of reflected light. We're not going to focus on refracted light just yet. This is just reflected light. So there's 4 main behaviors that we want to encapsulate within this integral. the first thing you'll want to look at is the integral itself. Why are we taking an integral? Well, an integral is essentially a sum. What do we want to take the sum of? Well, we're taking the sum of with respect to all incoming light. So let's say I wanted information on a specific point in space. Well, we know that this wall, if you have like something that's like my hand next to it, there's going to produce a shadow. And that's from some hemisphere around this single point. So one point is affected by all light coming from all directions reflecting off that one point. That's why we have to integrate over this hemisphere in order to take into account for all light coming from all directions. The second thing we want to think about is the material of said surface. So we know that some surfaces, like this wall, it's more of a diffuse or matte reflection. You don't really have these glossy, shiny spots, but if you look at the door handle, you'll notice that it's a bit more glossy. So using the BRDF, which stands for the bidirectional reflectance distribution function, we can sort of put these onto objects. So instead of having to define everything about the object, we can just be like, okay, this object is going to be diffuse, or this object is going to be glossy. And then when we project the rays into the scene, when they hit these objects, they'll use these functions and be like, okay, the light's going to be reflected either in a matte way or in a way that's shiny. The next thing I'm going to talk about is Lambert's cosine law, which is the dot product there. This looks kind of scary, I understand, but an intuitive way of understanding it is if you were to have something like a flashlight and you pointed it at like a piece of paper. If you point it straight down on that piece of paper, you'll notice that it's very bright. But if you were to tilt it to the side, it would spread out and become a lot less bright. So this is a way of sort of using or taking into account the angle at which an incident ray hits the wall and then goes off the wall. So you can think of this as it can be really bright, or at an angle, it'll start to dim down a little. And finally, this is probably the most applicable part, and the reason why this formula works so well is because it has a recursive definition. And what this means is that we can generalize this to all surfaces. So instead of using the rasterization method, where we would have to individually take into account every object and all its properties, we can instead just send the same equation and recursively go through the entire room on every object. So what does this really mean? So let's say we wanted to generate 3D graphics in a movie, especially if you think of like Pixar movies that have a lot of artifacts in the scene, like you have trees, you have characters. You don't want to have to define all these attributes for each thing individually. So instead, we can just create all of them with less details, and then just put these rays into the scene and have that do all the calculations for us. So now I'm going to start talking about a quick demo, so we have a bit of an understanding of how it works technically. If you have any questions about the specific implementation, feel free to ask me afterwards. But just for a general understanding, we know that we can generate colors on a screen using RGB values. So the red channel, the green channel, and blue channel, and you can combine them to make different colors. And using this formula from before, at each step, we get some sort of a factor that goes into each of these channels, thus telling us what color we need each pixel to be. So in this example, let's say we have this light ray. I know I said we're not projecting rays from light, but this is more of a way to understand how the equation really works. So we have this ray, it hits a door, and we know this door is blue, so that's the first thing we take into account is the color it has. The second thing we took into account, if you look here, is the BRDF. What does it take in? It takes in two directions, the incident ray, so the incoming ray, and the outgoing ray. Remember when I talked about the Lambert cosine before and how the angle at which a ray hits the surface and reflects off the surface affects how bright it is? Well, we can see that here. You can see that the values are dimmed a little from the original 10, 10, 10, and these factors go into 10, 10, 10 and brings it down to 2, 3, 9. So not only does it turn it blue, but it also makes it a little brighter, or not bright, but dimmer, but not as strong as the blue as originally, because it's going at an angle. And then eventually, we do the same thing. We would do the same calculation. It would hit the ground, and then it would come back to the camera. So this would be one chain of rays that we originally projected into the scene that we know hits a light, therefore must give us an image, and that goes to a single pixel, and that's the color of the pixel. And we would do this for the entire screen. So that's a quick understanding of how ray tracing works. But what's next? Where do we go from here? This process is already pretty expensive, and movies need to do this really quickly. And aside from movies, we also want to do this in video games too. So how can we do this in real time? That's another thing that people want to research. Also, another thing that I didn't take into account were refracted rays. So in surfaces that have a transparent element, so like diamonds or water or glass, some of you might know if you've taken a physics course on lights and waves, that they have refraction indexes, and when light hits them, they behave a little differently. So there is a way to implement refracted rays in ray tracing with Snell's law, but that's beyond the scope of my presentation. And so, yeah, I'd like to thank Professor Perovich for helping me with this project, and I'm open to any questions. Thank you.